So in the morning I was talking basically about physical characteristics of the system, just trying for you to understand better some of the fundamental characteristics. And I've heard from the discussions afterwards that it came as a surprise to some people that actually power systems are three-phase. Because if you model high voltage networks, you don't see it. But next time you're around and you see those big transmission lines here, you will be able to understand why is that. Oh yes. The big brother is listening and watching me. That's right. No, he's looking at the audience actually. Not really. But today I'll be talking about modeling. Doesn't seem to work. I didn't switch it on probably. Right. Yeah. So basically, I'll be talking about power flow equations. I mean, probably all of you who have dabbed into modeling, you've come across those power flow equations. For example, you know, I'm a co-author of one of the books, and you see equations of that size, kind of shape or form. So what I'll concentrate is to get you to understand what are the terms, especially what is the meaning of reactive power, because that's the issue which is often misunderstood. And also trying to understand what is, not only what is really reactive power, but how can you simplify those equations to the form that you can use in your modeling, because quite often this form of equation is not really applicable for mathematical modeling. And similarly, so I'll be talking about static modeling, just algebraic equations, but also dynamic modeling. And again, anyone who has done a little bit have seen the swing equation. So trying to explain what the terms are and why do we use some kind of complicated generator models as done by those differential equations on the right. So as usual, I will concentrate more on physical modeling, physical understanding, what is really what.
So we're not supposed to understand it at all?
No. I will try to explain to you why they look the way they look without going into fine details. And so my main aim, when you see those equations in the future, you will understand more or less where do they come from and what are the assumptions behind it and why do they look the way they do and how to use them, which is the main thing. Why do we have to use these high-order models, which will come at the end. So what I'll be talking about, the phasor analysis of AC circuits. Again, this is something first-year students do, but I thought it might be useful to revise it with you. Power flow equations, both AC and DC models, physical meaning of relay and reactive power, and the last part of the lecture will be about power system dynamics, about dynamic power system models. It means differential equations and different type of problems, steady-state stability problem, transient stability problem. So power system modeling. So if you look again at the network of the British network, at the end of the day, in graph theory terms, it's just a planar graph, just some links which connect nodes. So the nodes, which are buses, vertices, and branches, lines and edges. Well, some people ask, you know, why they are called buses? You know, they don't look like bus at all, but the full name is bus bar. This got abbreviated to bus. But of course, this is very simplified representation, as we've talked before lunch. Actually, that one of the buses, which means one of the points of connections, can actually be configured in different ways. So the whole topology of the network may look different than what it seems to look like. So there's not a number of engineering details. The size of the network, so this is high voltage transmission network. It means in this country is 275 and 400 kV. In the continent, the voltage level are kind of 120 kV, 220 kV, and I think 440 kV, something like that. And again, there was questions over the lunch. Why, for example, frequency is 50 Hertz? Why is there 3 phases, not 4 phases? This is a kind of compromise engineering judgment. I was talking about those 3 phases that you can remove the return wire. Could be 4 phases, but then it would be more complicated arrangements. You can do the same thing with 2 phases, but then the line-to-line voltage will be much higher. Why is 50 Hertz? and in the States it's 60 hertz. Historically, it was because you couldn't see the flicker on the bulbs. But you cannot see, so basically if it was 20 hertz you would see it. So that you have to be higher. Americans chose 60, we chose 50. Similar number. It creates problems. Voltages, well, you know that we've talked about it, that the higher voltage, the lower transmission losses. It means when it's transmission, you go into hundreds of kilovolts, for example. But whether, so the reasonable numbers will be about 100, about 200, and about 300, and about 400. But why is it, for example, this country is 275 and 400, and the Europe is 220, and I think 440, I can't remember at the moment. It's just the matter of judgment, normalization at certain point, and that's a kind of similar range, although they may not be exactly the same. So in Britain we have 810 nodes and 1194 branches, more or less, depending what model you use. In Europe, of course, it's the order of magnitude higher because it's a bigger network. So there'll be several thousands of nodes. So power stations, so in each of those blobs, red blobs, there'll be power station. It's modeled by differential equations if you are talking about fast changes. And this used to analyze power system dynamics. It means what happens when suddenly something changes dramatically. You have a short circuit or opening of transmission line. But for the steady state analysis, when everything goes normally from things change slowly, we use algebraic equations. So first we'll do static AC circuit analysis and then dynamic analysis. So the first question is how to manipulate AC voltages and phasors. So again, this is stuff which I do with first year students, engineering students, but I'm not sure if everyone knows about this, so let's go quickly through it. So the problem was that when the circuit analysis basically is applications of Kirchhoff's laws. It means you add voltages and you add currents to get balances. And well, both are sinusoidal, so there are some, of course, mathematical equations how to add two sine waves of different amplitude, but it's messy. So it's better to simplify it, and so Charles Steinmetz came with the brilliant idea to represent a sine function as a rotating vector, phasor. And then projection of the tip of the vector on the vertical axis will be a sine function. And because all those voltages and currents which are represented by those rotating vectors rotate at the same frequency, you can freeze them because relatively with respect to each other they're stationary. But there will be some angles between them. So phase shift between sine waves you can represent as geometric angles between two vectors. So it's very simple principle, and then you can simply apply Kirchhoff's laws to add those vectors or phasors. So here is example. So if you look at this red vector, it will move along, and projection on the vertical axis will give you a point which is moving along and give sine wave. So when you have a number of those sine waves, well, there will be number of vectors. As I said, they rotate the same speed. For some reason, Mr. Steinmetz came with the idea that they rotate anti-clockwise. I don't know why, but this is what everyone assumes. So with a given frequency and amplitude, I mean amplitude is actually in power circuit, it's not the amplitude, but it's RMS value, root mean square value, because that's to do with power, which will be the amplitude divided by root 2. And they will have a phase shift. Everything rotates at 50 Hertz or 60 Hertz in the state. So all you need to specify uniquely a current and a voltage is the amplitude and the phase shift with respect to each other, because they rotate at the same frequency. So the question is how to manipulate them.
So you just take the frequency as a constant, right?
That's right. So this is for steady state analysis. It means nothing changes dramatically. For steady state analysis when frequency is nominal. So when you have two sine waves, voltage and current, you can represent them, the arrow has missed here. So you represent them by those two vectors on the complex plane, and they rotate anti-clockwise. And you freeze them at any instant of time. So the time shift between voltage and current, the angle phi, is represented as the geometric angle between two vectors. So remember, this is a time shift, and this is geometric angle, and it simplifies manipulations. So I said the phasors are, and we call them phasors, not vectors, because it's the phase that is important. So they're stationary with respect to each other. We can add them as vectors or phasors. The angles between phasors are phase shifts between sine functions. And a phasor diagram is a snapshot of rotating phasors. And I'll give you an example how to calculate them. And because it's a snapshot at any time instant, it means that the reference is arbitrary. You can freeze them at any instant of time. So usually you choose one of those phasors to be your reference. It means its angle is 0, which is assumed on the diagrams usually is a horizontal line. It could be vertical or whatever. So all the angles are relative. So when you say that the voltage angle is 30 degrees, it means nothing. You have to say 30 degrees with respect to something else, because you have to always to specify reference. And of course, because they are vectors, so you represent them as complex numbers, because complex numbers are vectors on the complex phase. You have an equation which I use for students. I assume that you know it. Well, the most important thing, of course, is we electrical engineers use J instead of I as a root square of -1, because I is reserved for the current. But apart from that, all complex algebra is exactly the same in electrical engineering and in mathematics. And you have the fundamental equations. So on the resistor, voltage and current are in phase. So basically you have V is equal to R times I. But you can prove, I don't have time to go through it, but when you have an inductor, then the current lags the voltage by 90 degrees. So if you multiply current by J or I by a complex number, you shift it phase by 90 degrees. So there will be complex equation which represent the phase relationship between voltage and current on the inductance. XL is inductive reactance. For the capacitor is the other way around. It means current leads the voltage by J. By 90 degrees, it means you multiply it by -J. You move it in the opposite direction by 90 degrees. And the XC is the capacitive reactance, which is coefficient of proportionality between the two. And now the first example of complex phasor diagrams I mentioned. Please stop me at any time, by the way, remember, because I'm going quite quickly, because you assume that everyone knows it. But maybe that assumption can be slightly.
Are inductors and capacitors are physically different devices?
Yes. Inductors is a coil. Capacitors is basically you have two plates. Inductor is connected with magnetic field. Capacitor is connected with electric field. I'll talk a little bit later about it. Okay.
So we can think about a transmission wire as being a resistor.
That's the first order of approximation. I'll actually, sorry, people ask me questions, I tend to say, oh, this farther down the line in a few slides later, but it is, I'll just go through modeling of transmission line, because this is exactly relevant questions. So this is the first example of actually thinking about AC quantities as phasors. You remember I mentioned those phase shifting transformers, which I use as a control the flow of power flows in the network, especially to repel the loop flows in Europe. So this is example how they will work. So here look at those voltages. So what you have, so in the three-phase circuits, these are phase voltages. It means voltage on each phase of the three-phase circuits, 120 degrees shifted with respect to each other. So when you have three phases of the transmission line, and here you have the ground, so those will be those voltages between a phase and the ground, the neutral, right? So it will be those three phase voltages which are inside the triangle. But now if you look at the voltages across them, it means line-to-line voltages, which are named line voltages for some reason in power engineering, which is of course between the vertices over here. Quite clearly that line voltage is 900 degrees at right angle and quadrature with respect to the phase voltages. 90 degrees, sorry. Which means that basically that generally speaking those phase-to-phase voltages, line voltages, are in quadrature with respect to any of those respective phase voltages. And now how we can use it. So when you have a transformer, Well, I showed you the picture of transformer. So transformer will give you will some voltage which is proportional to the voltage on the secondary. Will have some voltage which is proportionally to the voltage on the primary side. So if you connect them in a clever way, the primary voltage, primary winding will be across the phase voltage, but you connect it. The primary will be not the phase voltage, but it will be the phase to phase voltage. It will be at 90 degrees with respect to the phase voltage. So then when you connect that transformer in series with your transmission line, it means you connect it. If this is transmission line, you take this voltage and you add it over here, then we will have the diagram which is on the right. So normally, let's go first through this one. So normally this is for the normal transformer when you think about it. It means this is the transformer, and if you connect additional winding, it will give you voltage which is in phase. So it means it will increase the magnitude of the voltage. So you can increase the voltage. But if you do this clever arrangements, it means you add to each phase over here a component which is not in phase, but it's at 90 degrees, which means you add to this one, you add to this one, that one, there will be that component. That means you don't change so much the magnitude, you change the phase. And that's why they are called, in England for example, they are called quadrature boosters, because that voltage is in quadrature with the phase voltage. So there are phase shifting transformers, because if you look at it, this is the original voltage. If you add the voltage which is at quadrature, you change the phase shift, you change the phase angle. Adding a voltage in quadrature changes the voltage angle and therefore power flow. In a few slides later, you will see that the power flow is proportional to the sine of the angle between the voltages. So by changing the nodal voltage, you change the angle. By changing the angle, you change the power flow to some extent. So this is the principle of those phase shifting transformers.
Could I ask a dumb question? And you answered it this morning, but you have three phases here. So is a transformer to try physically to move from one phase to the next? That's the reason of having the transformer in there.
So normally transformer looks like that. So you have a primary winding and you have a secondary winding, right? So transformer across, so you change that's the voltage. This arrangement is slightly different because what physically is, so let's say you have three phases. So what you do, your primary winding will be here. So it will take the voltage which is across between phases, so which is in quadrature at 90 degrees with one of the angles, but its secondary winding will be here of the same transformer, right? Which means that you add that voltage over here, multiplied by A is transformation ratio, right? So you add the this voltage to the normal line voltage. This connection physically is in series, but because that angle is 90 degrees, that means you have this component which changes the phase angle, the voltage angle. By changing angles, you change power flows, as I will show you a few slides later.
So physically, in the ordinary transformer, the two wires are sort of physically separate, two different wires. But here, you're winding one wire sort of around twice. You've really got the same wire. Yeah.
So normally you have a separation.
Yeah.
Here, because these are the kind of parallel, those two wires are in parallel. While here, it's in series. You add a component. You add the component of the voltage in quadrature. That's where you can shift the phase. Okay? So this is the principle of those phase shifting transformers. So, but you don't really physically change the power flow. You just change the angle slightly, which will affect power flows, right? Because there was a question earlier on about if you can do it. Yeah, and I showed you that diagram before the lunch break. So basically, those phase shifting transformers over here and those over here, which are not shown over here, will affect the angles at certain nodes. So they'll try to push those red arrows inside over here by changing the angles.
So can I, so to reflect on this, you really, to fix that problem in Europe, you really need to go to the three-phase model.
No. Well, you can represent it by single phase. Sorry. You need three phase in order to understand why is it at 90 degrees. Why is it this one component, right? Why that component is 90 degrees. But then you can do the whole analysis just using on one phase, right? So you forget. I'm trying to explain to you why physically how it is done. But for the purposes of modeling, everything, assuming that everything is balanced, you just calculate one phase. That's enough. You don't go into physical details how you do it. You need to. So those are good questions. I should have put them on the slide. You have to, in order to understand, you have to understand that arrangements of those phase shifting transformers is completely different than the arrangements of normal transformers. Okay? Right. So now we come into this concept of real and reactive power. So power is a product of voltage and current, and then we can represent them as complex numbers because we are working with complex numbers. And general equation is that the quantity S, called S, which is apparent power, is equal to voltage times conjugate current. We use conjugate current because of interest for us is this angle between voltage and current, angle phi. So if you multiply voltage by the conjugate current, complex conjugate current, it means we look at the differences between the angles. This is for complex numbers, right? And then we separate that quantity, that complex quantity, into real part and imaginary part. We call this one P, and this one we call Q. So real power is VI cos phi, where once again phi is the Einstein power factor angle between V and I. And reactive power is VI sin phi, is imaginary component. And people do those calculations all the time, but even power engineers don't really understand what reactive power is. People understand what real power is because it's energy. It's obvious. Reactive power is a little bit like real power, but it's actually completely different. And so real power represents energy used in the network, but the question is, what is the physical meaning of reactive power? And if you talk to power engineers, they will use a lot of silly analogies. So people use tandem analogy, horse boat, you have different examples, trampoline, drying line analogy. Some people like this foam on the beer analogy, which I could never understand. Apparently you need foam in order to drink beer, but any Englishman will tell you it's rubbish because English beer has no foam.
Any southern Englishman.
All of a sudden, oh, here is it. Chris, would you consider yourself southern or northern? Manchester is north, isn't it?
Yeah, well, they certainly serve beer the northern way.
So it's a long-going discussion about it. And I think all those analogies are completely silly because there's a very simple explanation of what reactive power is. So that's what I'm trying to explain it to you. And that gives into the concept of inductances and capacitances. So there is inductive reactive power and there's a capacitive reactive power. Reactive power is always when we have an angle between voltage and angle. They're not in phase. I'm not allowed to get through it. So what is inductance? Well, any motor, any generator will have some coils because you need coils to produce magnetic field because it's all based on the Faraday's law principle. You need some magnetic fields. So in the circuits, well, this is representation. So there's a coil which has some inductance. Idle coil will have resistance equals 0. There is a voltage and current, and the angle between them is 90 degrees, which is important. I'll not go through it. Why is that? But basically, this is due to the effects of the magnetic field. So motor is an electromagnetic device or generator and needs coils to produce magnetic field. Now, because current is alternating, AC, it means that energy to supply this magnetic field means energy. Electric field also means energy, but it's electric energy. So when you talk about magnetic field, the current goes to the field, half of the cycle, a quarter of the cycle, and then quarter of the cycle goes back. And then it goes in the opposite direction. So current oscillates between the source and that particular motor. That means that when the current is increasing, so here we have the voltage and here is the current, are shifted by 90 degrees as is the case for the coil. So when the current is positive in half of the cycle, that means that it flows from the source to the motor. It means the magnetic field of the motor increases. It sets up its magnetic field. And then the other half of the cycle, the current goes back from the coil to the source. So the current is decreasing. It means the energy is sent back. The coil sends back energy, demagnetizes itself, and sends back energy to the source. So what you have power energy exchanges between the coil and the source. When current is positive, the coil gets magnetized. It increases its magnetic energy. When current is negative, it demagnetizes. It goes back. So we have continuous exchanges of energy between the source and the coil. And that energy is called reactive power. So remember that because current carries, of course, energy, and the power supply in magnetic circuit is current times voltage. And remember, the current lags voltage by 90 degrees, as it is the case on this diagram. So the frequency of energy exchanges is 100 Hertz, because everything it repeats itself half in each cycle. Energy is always positive, I squared times x Li squared divided by 2 in terms of the coil, where L is inductance. So here you have again voltage and current shifted by 90 degrees, and that red line is the product of the two. So you can see when the current when the current is increasing, the energy flow is positive. When the current is decreasing, the energy flow is negative, and it repeats itself twice every cycle. Okay? Once again, current is increasing. Sorry, here's current, blue current. Current is increasing. It means the product is positive. It means the coil is magnetized. Here current is decreasing. It means power flows in the opposite direction. It means it demagnetizes itself. And it repeats twice in every cycle, whichever direction of the current. So you have 100 Hertz exchanges between source of the coil. So that oscillating energy is termed reactive, or imaginary, or idle. It's not idle because it's needed, but it cannot do any work, because if you take average over the cycle, it's 0. But you need it there because otherwise you wouldn't have magnetic field, and basically the motor wouldn't work. So reactive power, that's why people are using, like a foam on the beer. You need it to make beer good, but it's rubbish because Southern English drink flat beer. Yes, but
So then what do you, reactive power support, like you need to support, like if I hear this terminology, what do I ignore it? Because like reactive power support sounds like foam supporting the beer.
Well, but there's an argument we go between Southern and Northern England. The Southern Englanders think that foam is completely unnecessary, and all those,
We all agree that the Dutch shouldn't be carbonating it.
That's right, but the Dutch even worse because you carbonate it, so you have more even physics stuff, right? So that's why I'm saying it's ridiculous. Reactive power is needed in networks because you need coils, and without coils your motors wouldn't work. If the network was purely resistive, you wouldn't have reactive power.
What is a resistive network?
Resistive network means wires will have no inductance or capacitance, straight wires. As long as you have coils, you have immediately inductance. Okay? And of course, you have AC, we'll come back to it. Basically, so that phenomenon exists in AC networks only. If a network is DC, current is constant, which you don't have those exchanges of energy between the coil. Coil will get magnetized and it will stay magnetized.
So what does it mean then if you hear, for example, solar panels produce a lot of reactive power? Is that rubbish?
No. Yeah, that's complicated argument. The solar panels themselves produce DC power. But what are connected to the network, because the network is AC, they are connected by inverters, which change DC into AC. And now with that, those inverters, which are power electronic devices, you can program in such a way they can control the phase shift between the voltage and the angle. And by controlling the phase shift, they can control reactive power. Okay?
If you look at the power flow equations, then you see the voltages depend a lot on the reactive power.
I'll come back to it in a second, yeah. So this is important to understand it. Okay? So yeah, I'll come back in a second to that one. So this is the point I've just made. There is no reactive power in DC circuits because current is constant. So you don't have those exchanges of energy. And now capacitive circuits. Capacitive circuits, everything is exactly the same, but it is shifted by 90 degrees because the capacitive current is 90 degrees ahead of the voltage, while inductive circuit, it was the other way around. It was delayed by 90 degrees. And it's connected with the voltage. Because capacitors need energy to supply the electric field. So if you have a capacitor, there is a voltage across them, and there is some stored electric energy in the capacitor. And that electric energy is proportional to the square root of the voltage. C V squared divided by 2, C is capacitance. And now will be exactly the same as if with inductors, but that connected with the voltage. It means when the voltage is increasing, it means capacitor gets increases its electric field. When voltage is decreasing, it gives back this energy needed to set up its electric field. So it is the same thing, but connected with the voltage rather than with the current. So this is what I just said. So basically, but that means that those energy oscillations are directly in the antiphase. Because if you take, because on the inductor, current is 90 degrees behind the voltage, and on the capacitor, current is 90 degrees ahead of the voltage. That means that the phase shift between them is 90 plus 90, 180 degrees. It means they operate exactly in the antiphase. And because so this is the point I just made, and because they act opposite the antiphase, it means they compensate each other. So that's why we're talking about reactive power compensation. It means in inductive circuits you connect capacitance to compensate it. And so the net effect will be basically a difference between the two. And then when people are talking about reactive power sources and sinks. But remember that the average is 0. That's why I put inverted commas. So inductance is reactive power sink in inverted commas, and capacitors is in reactive power source. This is a pure assumption. You may assume the other way around, because there is no such a thing as source and sink of reactive power. The average is 0. You just need them to compensate each other, and it's just your assumption whether you assume that one is the source, the other is a sink.
Also reactive power, can some of it get lost?
Sorry?
Can some of it get lost, or is it?
You have some exchanges. There will be losses. I'll come back to it in a second with respect to those exchanges. I'll come back in a second to that. So that's why I said capacitors and inductors compensate each other perfectly. When one needs energy, the other can deliver it. That means if you connect capacitors of exactly the same reactance next to inductor, if you look from the outside, they're not there, because they will compensate each other completely. But there will be energy exchanges between them. So that piece of wire which connects them, they will see changes. But if you look from the outside, there is nothing, because they perfectly compensate each other. A few equations. So real power is the average power over a cycle, is VI cos phi. Reactive power is VI sin phi, because that simplifies equation, because if one is cos, the other is sine. For reactive power, you cannot take the average, because average is 0. Vi sine phi, you can show in the equation, is the amplitude of those energy exchanges. So that's why it quantifies the amount of reactive power in the network. Vi sine phi. A real unit of real power are watts. Reactive power is volt amperes reactive, VARs. And apparent power, which has no physical meaning, it is just voltage times current, or root square of P squared plus Q squared. But apparent power has no physical meaning. Real power has meaning, reactive power has meaning. Apparent power is a useful quantity in circuits, but it has no physical meaning as such. So power factor is the ratio of real power to S, or P to P squared plus Q squared. It is just a quantification, is a measure of how reactive power is, and we are talking about power factor equals 0 when circuit is purely reactive, carries no real power, and power factor 1 is in the circuit is purely resistive and carries no reactive power. Generally, you try to achieve a circuit to be as purely resistive as possible by means of compensation. It means you try to get power factor close to unity, and I'll show you in a second why is that. Any questions? So now I'll tell you why reactive power is nasty, why we try to get power factor close to unity. The first thing is that we said the average exchanges are 0, but the power flows back and forth, and whenever power flows in the network, it causes real power losses. So when you have reactive power loads, there will be real power transmission losses on the wires connecting them. And of course, real power losses, you pay money. So you try to avoid this. So this is one of the reasons for compensation, just to spend less money on transmission losses. Second thing is it takes up capacity of wires. Well, wires are designed to carry certain amount of power. If you have a transmission line, for example, and of course you want to make that capacity available as much as possible for real power transmission. If the transmission line transfers reactive power, it means it will get heated. It means less capacity is available for your real power transmission. The maximum capacity of the transmission line depends on the transmission losses, heating limit. Second thing is reactive power. This is something what Bert has raised, and I'll talk about it in a second, is that when you have reactive power, that affects voltages. But I'll prove it to you in a few minutes. At the moment, I just mentioned it. When you have reactive power transfers, your voltages drop. But I'll explain it in a second. And because the voltages drop, it means you cannot transfer power over long distances. Real power, here in England, you can transfer it from Scotland. This is no problem. You cannot transfer reactive power from Scotland to here because voltage drops would be too much. And as I said, I'll explain to you in a few seconds, in a few minutes. So main sources of reactive power in the network are the synchronous generators. I'll show you later on why is that. So your generators, depending of the value of so-called excitation current, can be either sources or sinks of reactive power. Usually operate them as sources. But also transmission lines may produce them. I mentioned the problem of the voltages before the lunch break. So, and you may have additional compensation by capacitors. And quite often in transmission networks you have those capacitors which are connected in order to produce reactive power, to compensate the inductive reactive power. And if you don't have enough reactive power in the network, it may lose to the voltage collapse, because the voltages drop too low, and at one point you have what is called voltage collapse. I don't have time to talk about it in details. So it is important to compensate for reactive power. So now, again, there was a question about how to represent transmission line. AC transmission line. If you have a DC transmission line, it's simple, it's just resistance. Because for DC current, all you have is a piece of wire which has certain resistance. You apply the voltage, current flowing through it will be equal to the voltage difference divided by resistance, and this is it. Because it's AC, you will have inductive effects and you will have a capacitive effect. That means that the full model of the transmission line which is one of those things, will have resistances, which is obvious because it's a wire, it will heat up, the wire has resistance, it will have inductance and it will have capacitance. Now why does it have inductance first of all? Now if you look at those wires, there are no coils on them, but those wires are quite close to each other, and the magnetic field which is around each of those wires, and interactions between magnetic fields of those wires will cause this inductive effect.
So there are different phases. Those wires.
There are different phases.
Ones that are close to each other, deliberately close to each other, and different phases.
Well, but it's called self-inductance as well. So I mean, even if you have a single wire,
Right.
single phase circuits, you have AC current, it also will have inductance. So we're talking about the self-inductance, which is wire magnetic field due to its own, and also mutual inductance when you have two wires, as it is here, you know, two phases, okay? And that inductance depends, the inductive effect, this is magnetic field, and magnetic field is due to the current. And that's why inductance, which is that thing over here, is in series. Because the stronger the current flowing through that line, which is current I, the stronger the magnetic effect. So that's why transmission lines, we model inductance in series with the resistance. Once again, this is single phase representation of a three-phase circuit. So this is a line, and this is the return wire, which remember in the proper three-phase circuits, return is 0. But here, because we represent one phase, so we have to provide return. This is just for mathematical modeling purposes. So this is resistance inductance. Now what about capacitance? Capacitance normally means you have two electrodes right next to each other. And if you look at it, you have electrodes because you have, this is one wire, this is another wire. So there will be some capacitance between the wires, and there are wires and there is a ground at 0. So again, there will be some equivalent capacitance between the wire and the ground. But those effects are between, not in series, but between wires and between wires in the ground. So that's why it's represented on the equivalent circuit as a capacitance between the wire which flows the current and the return. So that's so-called shunt. Here are connected kind of half of it here, half of it there, because we represent this is equivalent circuits of a long transmission line. So in order to represent that it's kind of distributed effect, we put half of a capacitance at the beginning, half of it at the end. Equivalent representation. So this is so-called pi equivalent circuit because it forms letter pi. Okay? Questions? So this is the full pi equivalent model of a transmission line, but of course we use simplified models generally speaking, unless you want to model absolutely everything. So let's go through this model. So first, so R is series resistance causing heating losses, X equal omega L, L is inductance, omega is equal to pi F is the series reactance due to the magnetic field it consumes, Q, and omega C, BC omega C, which is 1 over XC, is shunt susceptance due to electric field. So reactance will be 1 over omega C. Just easy to represent as the inverse of that due to the multiplications. But it's the same thing. So remember, so the capacitance will produce reactive power, the inductance will consume reactive power. And I mentioned, I can't remember, was it the lecture or break, and I said, no, I think during the lecture I said that transmission system operator will switch off some of the lines at night. Now why? Because during the day there's high current flowing over here, it means inductance is very high, the inductive effect is much stronger than the capacitive effect. So a line is a net sink of reactive power. Voltages go down. At night, that current is very little, very small. It means the inductive effect is small, but voltage is more or less the same, so capacitive effect is strong. And at night, it may be that the line is a net source of reactive power. It produces reactive power, which lifts the voltages up. I'll show later on why it lifts voltages up. So that's why sometimes they switch off transmission lines because this capacitive effect is too strong and raises voltages too much. Okay? Clear? Now for modeling purposes. As it happens, if you do the calculations for high voltage transmission lines, transmission circuits, X is much stronger than R. So as I'll show you some models, some simplified modeling, it will be about 5 to 10 times bigger. We may leave just X and forget about R for very simplified analysis. For distribution lines, R and X are similar order of magnitude, so it means you cannot just represent line by X. You have to model both R and X. And usually for both transmission and distribution lines, you may forget about capacitance for the simplified analysis.
So can I ask, earlier on we talked about why you use high voltage transmission. You said because of I squared R losses. But now you're telling us to neglect R completely. So I don't understand.
No. This is about details of modeling. Generally you cannot. For some very simplified models, so-called DC analysis, I'll come back to it in a second, you can model it when you're considering just real power flows. Okay? So this is just for modeling purposes. Simplified modeling purposes to get your models linear and nice. Okay, but generally, yes, you are right. I mean, if you use accurate models, you have to model everything. So just levels of approximation.
When I gave my first ever lecture in Edinburgh, Ken McKinnon was in the audience, and he asked me a version of that the flow limits may well be because of losses, reactive losses, but we're receiving in DC model there are no losses. I had to think about that one afterwards, but my answer was that it's simply in the case of looking at flow limit, there's nothing bigger going on. Whereas when it comes to thinking about about the direction that power flows take, there is something bigger.
And I'm sorry, I keep giving the same answer. The answer will come up in a few slides later. And then please stop me if you still don't understand it. So now let's look at approximation. So now, as I said, for both transmission and distribution lines, if you use just resistance and just reactance, it's generally fine. For very simplified models, which I'll cover in a second, so-called DC model, we just leave reactance. We forget about resistance because X is usually 5 to 10 times bigger than R, but here there are no transmission losses. That means the disadvantage of that model is we do not model transmission losses, right? But for some analysis it is useful. But if we look at the cables, we have to use full underground cables. We have to use both. We have to use also representation of the capacitance, because if you look at the cable, it's running underground. The cables themselves are close to each other. Transmission lines, they're several meters apart. And around it is earth. So the distance is very small. Overhead transmission lines, you know, the lines are several meters up. Because the distances are small, it means capacitive effect is strong. It means that effect of capacitance is actually very strong. And that means that it creates there'll be quite high current flowing through those equivalent capacitances. And that's the reason that underground cables, AC cables, cannot be longer than about 10 kilometers. Because the capacitive current would load up the cable. There will be no capacity in it, heating capacity, for real power. So that's why underground AC transmission cables are used in cities, because you cannot run transmission lines over houses, but they're short. They'll be just a few kilometers. If it's too long, capacitive effect will take over. Okay? So as I said, longer cables must be DC. And this is the reason why in Europe we've mentioned that underground cables. So the connections, those blue ones, are connections between countries. So there are cables running underwater, undersea, and for that reason, if they were AC, they would be loaded by reactive power. There will be high capacitive current, useless. So that's why those cables have to be DC.
Not to do with the water.
No, basically they run underground.
Put it underneath a mountain.
It's the same thing. It's just the question that the ground is around it. It's very small distances, right? Well, they have additional effect which I mentioned before. They separate from the frequency control point of view, but the main reason is physical, is technical. Those cables which are the length of tens of kilometers cannot be AC because of the capacitive current effect. They have to be DC.
And DC also has disadvantages.
Well, everything has advantages and disadvantages. Basically, from the transmission capacity point of view, you can transfer more across DC than AC. So the people are talking, for example, it's difficult to build transmission lines in Europe or the States. So there are some, I saw some designs where basically you can transform the existing AC transmission line into DC, and you could flow more. You can transmit more power across it. So usually there are no DC networks and such. There are just connections between AC networks which are DC. Any other questions?
So what do you think about this hybrid grid? Like there's this company DNVGL. They really think that, for example, within Germany we will have lots of additional DC cables too.
Well, the reason which, as I mentioned, so you can first of all, it's, as I said, it's impossible to build new overhead transmission lines in Europe. The last new transmission line in Britain was built 20 years ago, and it took about 20 years to build it, to overcome all the planning permissions problems. Even reinforcement, the existing transmission networks. Chris's parents lived near Beaulieu, which was famous Beaulieu-Denny line, which was basically existing line. They wanted to increase the voltage in order to transmit more power through it. Huge planning objections. People were protesting against it because part of it ran through the national park.
You're going to have to add more cables, lines, because of the wind parks.
So that's why they're saying, in Germany there are those problems, as I mentioned, loop flows around. Transmission pattern has changed because they have a lot of power in the northern Germany, wind power. They need to transmit it across to the south, where on the industries. So they say, okay, why don't we use the existing AC lines to do it? Or, for example, I saw some plans, we can run DC cables underneath the motorways. Okay, so that would be example. As I said, if you use the underground cable, it has to be DC. So that's why they are talking about those DC. So it will be this overlying network of DC on top of the existing AC network, just to get power across. But it's not a DC network. It is just additional DC connections. Okay? So now let's talk about those simplified power models. So this is your question. Why can we forget and why not? So first of all, the fundamental power law is the Ohm's law. Voltage is equal, current is equal voltage divided by resistance, or by the impedance, which is linear. Easy to analyze. The problem with using that model is that it's voltage and current. Both are AC, which means, and AC has no direction. So if you say that the current flow, AC current flows from here to there, it's rubbish. The average is 0. But energy does flow from A to B. So that's why power engineers tend to think not in terms of current, but in terms of power, because power has direction. So all the equations will be real power, reactive power, rather than current, because that's physically what happens. So full AC equations are complicated. So the question is, I'll concentrate on those simplified models which are used for cause-effect analysis and for mathematical methods. So what I will prove to you now is that real power is driven by the angle difference. That was the principle which was used for those phase-shifting transformers. And then the reactive power is driven by the voltage magnitude difference. So I'll use a few equations to show it to you. But I think it's nearly 3 o'clock, so perhaps before I go to that, let's take a break, okay? And you can free to ask me questions. Yeah, so 3:10, we gather again. What our task at the moment will be just to get some simplified equations which do not use the full model, but some simplified model, and in order to simplify the equations, especially to get the linear models. So the most simplified model is for the modeling of the transmission line. We just assume that the only thing relevant is reactance, because it's about 5 to 10 times bigger than the resistance, so we forget the resistive effects. It means we do not model transmission losses. So this is approximate analysis. From my point of view, it's useful in order to understand, because that allows you to derive some equations. You can get a better understanding. But it's no near exact modeling. And then I'll also use the simplified circuits to show you example of the phasor diagrams, how you construct phasor diagrams in power circuits. So let's assume that you have just a reactance. This is the voltage at the receiving end, VR, voltage and descending and Vs. Remember, this is a single phase representation of the three-phase AC circuits. So everything here is AC. This is the current I flowing over here. So I'll show you how to build a phasor diagram, because I will need a phasor diagram to derive some equations. Everything here are phasors. It means they rotate at 50 Hertz. They can be stopped at freeze at any time. So it means the reference angle is 0. So let's freeze it that the voltage VR is at 0 angle, reference. So this is the reference. So this is the voltage VR at angle 0. And then let's assume certain position of the current I. Typically, those circuits are inductive. That means that we assume certain lagging power factor, and let's assume that the position of the current I with respect to the voltage VR is like that. Everything rotates anti-clockwise. So it means that the current is lagging the voltage, which is inductive circuit. So let's assume it looks like that. And now let's try to calculate the voltage Vs, build up the voltage Vs. So Vs will be VR plus voltage drop on the inductance X. But remember that here is 90 degrees delayed. That means that the voltage drop on the inductance X is 90 degrees. This is the current. It means voltage will be 90 degrees ahead of the current. Voltage Ix, voltage drop over here, will be 90 degrees ahead of the current. So it means it will be this direction, and because Vs is equal VR plus Ix, I've added the vector. This is the way you add the vectors, of course. I put the vector Ix, start here and over there, and the total vector Vs completes the triangle. So this is how you build typical phasor diagram. So this is the angle phi, which is the angle between voltage and the current. If you do the triangle, the same angle is over here. So let's derive the equation. So this is the equation for that circuit in the complex numbers. I signifies that the variable is a complex. And just solving the simple triangles, Ix cos phi, this is Ix cos phi, which is the perpendicular element from the small triangle. If you look at the big triangle, it is equal Vs sine phi. So while Ix sine phi, which is this one times sine, which is that element from the big triangle, is equal Vs cos delta minus V. So we have two equations. And then when multiply them, separate the terms, remember that P is equal Vi cos phi. So this is the equation, that P is equal Vs times VR, sending times receiving voltage divided by X, multiplied by sine. Q, it will be something similar, Vs VR times X multiplied by cos delta minus VR squared divided by X. So we have moved now from representation of real and reactive power in terms of the voltage and current, Vi cos phi, Vi sine phi. We represent everything with respect just to the voltages and the sending and the receiving end. Okay? Simple trigonometry. That angle between voltage, sorry, this is from wrong slide. Angle between VR and Vs, it should state VR and Vs, is called the power or load angle, and basically drives the flow of the real power. And do not, so this is the angle delta. Do not mix up with the angle phi, which is between voltage and the current, which is the power factor angle. So delta is the power angle, this is the power factor angle. So we have equation V, real power is equal voltage in the sending end, voltage times voltage the receiving end, divided by the reactance multiplied by sine delta. And now, which means we have 3 variables over here on the right hand side. But 2 variables are not really variables. For simplified analysis, we can assume that they are constant. Because the voltages in transmission network have to be relatively constant, plus minus 10%, because voltages over here have to be constant at the distribution level. So the voltages at transmission level cannot be all over the place. They have to be relatively constant, plus minus 10%. So again, for simplified analysis, we can assume that Vs and Vr are relatively constant. That means that the flow of the real power will depend on the angle delta. The higher power flow, the higher the angle, the phase shift. Once again, let's look at the previous diagram. The higher phase shift between Vr and Vs. So the real power flow is not dictated by the voltage magnitude, Vs, Vr, but by the angle between them, as the sign of the delta.
So the del is negative, it goes in one direction.
That's right. So that means if power flew in the other direction, Vs would be down over here. Angle will be negative. Okay? So real power flow, once again, depends on the phase shift between the voltages at the sending and the receiving end. So of course the maximum, so immediately we get that the maximum value of the angle is 90 degrees. This is steady state stability limit, and this is quite reasonably realistic model in the whole operating range. So when you are looking at the simplified power network models and you are interested only in the real power, this is quite realistic assumptions. That gives about 10% accuracy. And it's important that it is valid in the whole operating range because we have sign over here. And remember, we cannot use it in distribution networks because we forgot about resistance. So that model is only valid in the transmission level, high voltage level. It's not valid at the distribution level. And of course, because it's angle sign, so we can immediately get the linear model if we assume that the angle is small. And the angle has to be small because 90 degrees is maximum, and they have to be, so if it goes anywhere near 90, you will lose stability, so we try to keep angle small, below 45 degrees. So if we assume that the angles are small, we can get the linear model. And now, if we assume that the voltages are constant and are equal to the nominal values, so if we divide voltages, Vs and Vr, by their nominal values, then they will be equal to 1, more or less. So Vs and Vr in per units, when you divide it by the nominal values, are 1. So we get this linear equation that the power is equal to delta divided by x. So this is a linear model. And now, why the confusing name DC model? So this is referred to as the DC model, which of course some people confuse with the actual DC networks. Has nothing to do with the actual DC network. This is an AC network. But now why is it called DC? Because in the actual DC network, current is voltage divided by resistance. Here, in the DC model of AC circuits, power is equal to angle divided by the reactance. So you have a linear relationship, right? So instead of current, we are talking about power. Instead of voltage, we are talking about the angle delta. And instead of resistance, we are talking about reactance. So this is the linear model. But remember about strong simplifying assumptions. First of all, resistance and capacitance neglected. But secondly, it's only for small values of the angles. So if you use linear model, you cannot model anything approaching stability because the angles will be high. Linear model is stable in any range of angles, while if you go in the big angles, you may lose stability if angle go anywhere near 90 degrees. Usually they're below 45 degrees. But because it's linear, people love it because you have all the simplifying assumptions. So this is the DC linear network model. Questions?
So when you talk about per unit, so we have a nominal value, does that somehow get sucked into the X?
Yes, but I just, of course, you have to do per unit, means you have to transformation of all the variables. But
Right.
so X, you're right, X also would be in so-called per units. It means divided by some nominal value. Power networks, usually we use those per units because it's easier. Because you know the voltages are equal to 1, and it kind of simplifies the notation. but you don't have to. I don't go into that because it's
Right.
a little
But
bit
we could
complicated.
leave the x and just have some constant.
Yeah, that's right. So you are right. So in this equation, x will be in ohms. In this equation, x will be in per units. Now let's look at the approximate model when we have both reactance and resistance, and we'll use model mostly for the reactive power flows analysis. Okay. So now we are neglecting still capacitance, but we have both resistance and reactance. And what we are interested in the voltage drop. It means voltage difference between voltage at the sending end and voltage at the receiving end. Not complex voltage difference, including the angle, but just difference in terms of magnitudes. One is 240 kV, let's say, and the other is 230 kV. Just the difference in voltage magnitudes. Because remember, the complex numbers are mathematical fiction, right? What if you stick voltmeter in the network, it will measure the magnitude. So this is what we are interested in, is the actual voltage magnitude. So what we are interested in is the arithmetic difference between the length of those two phasors, Vs and Vr. So now again, let's do the phasor diagram, but with including the resistance. So again, we start with Vr. Again, we assume the angle I, but now Vs will be Vr plus Ix plus Ri. Xi is 90 degrees with respect to the current because it's reactance, but Ri will be in phase with the current. So this is the current, we'll have both components, and now we have to add to the vector Fi because Vr plus Xi plus Ri must be equal to Vs. So we are building this relationship. First we are adding resistance the voltage drop Ri, which is in phase with the current, so we are adding a component which is parallel to the current I. So this will be Ri, and then as before we add a component which is at 90 degrees ahead of the current, so this is voltage Ix, and the sum of the two will give Vs. So this is how you build the phasor diagram. And now we will use this phasor diagram to calculate the difference between the length of Vs and Vr. So we are not looking at the vector phasor difference, but the magnitude difference, arithmetic difference. This angle delta. So this is the diagram once again, and again some simple trigonometry. Again, delta Vq, it is equal to xi cos phi, which is that one. So this is dg minus be, and be from small triangle is equal to ri sin phi, and delta vp, which is that component over here, delta vp, it is equal ri times cos of the angle phi, here is angle phi, plus xi sin phi. Sorry, sum of those two components, not plus, not minus, plus of those two components. Simple trigonometry. Again, P is equal to Vi cos phi, Q is equal to Vi sin phi, which means that the delta, we can calculate the delta Vp from the first equation, substituting here, getting rid of those cos phi's and sin phi's by P and Q. We get equation for the voltage difference along the P axis, which is this one, and along the Q axis, which is this one, vertical. But angle delta is small. Remember, for steady state stability reasons, we can assume that delta is small. It means that the difference between the length of those two vectors is roughly equal to delta Vp. We neglect delta Vq. If we say so that it is equal to the delta Vp, it means we are left with this equation. So that means that the voltage difference between voltage in the sending and the receiving end is approximately equal R times P plus X times Q divided by VR. And this is a very important relationship because it shows you how the voltage differences between nodes across the transmission network depend on the flow of real and reactive power. So both flow of real and reactive power will cause the voltage drops on the network. But voltage drop due to the due to real power is proportional to R, but voltage drop to the reactive power is proportional to X. As we said, in transmission networks, X is much bigger than R. Because X is much bigger than R, it means that the flow of reactive power is dominant in terms of voltage drops. And that's what I said that before, that the problem with reactive power is causes voltage drop across the network. This is due to that relationship. Right? So, although you may have big real power transfer, but R is small, so it doesn't matter. If you have equally big transfers of X, voltage drop would be different. So you cannot transmit power. You cannot have large reactive power transfers. Reactive power has to be compensated locally, supplied locally. If you are in Cambridge, it has to be done around Cambridge. If you are in Scotland, it has to be done in Scotland. You cannot borrow reactive power from your neighbors, because that would require huge voltage drops. And that's why I said at the beginning, real power voltage angles, reactive power voltages. Those do fundamental relationships. They go close together. Of course, there are cross terms, but they're small. So once again, the flow of the real power depends on the phase shifts between the voltages and the sending and the receiving end, angle delta. Reactive power flow depends mostly on the flow of the reactive power. And as I said, reactive power cannot be transferred over long distances. Questions?
Just to sort of help me be clear about this, when you talk about reactive power being transferred over long distances, would it be fair to say that that's a bit like saying that the inductance and capacitance have to more or less match locally?
Not only that.
Not only that.
Well, because you can compensate if you have, let's say, big inductance. Because what does it mean, big inductance? Big factory over here, right? In Cambridge, let's say. You have a big factory which has a lot of motors, so they require a lot of reactive power. There are two ways of doing it. Either you put big capacitor next to it, or you have a generator, power station, and you manipulate, I'll show you later on, you manipulate so-called excitation current on the generator in such a way that it produces reactive power. So that reactive power to supply this big factor in Cambridge can be done at the generator, which is close. The key word is close. So always two ways of compensation, remember. Either you have capacitor, but then you need to invest money into it, or it's far cheaper, you change the excitation current on the generator. It's much cheaper way of doing it. Okay? Other questions? And the last point is about wind, generally speaking. So as I mentioned, traditionally those power, both real and reactive, would flow from generators down to the loads. It means reactive power on the distribution network would flow from the top down. That means that the voltage will be high at the substation at the beginning of the feeder and be lower at the end of the feeder. What happens when you put the wind farm at the end of it? When you put wind farm at the end of it, you change that P would be big, but will be negative. It will flow the opposite direction. So you may have the effect, the inverse, that the voltage would rise rather than drop if you look across the distribution network. So at the end of the network, voltage would be too high. And again, it exceeds the limit. This is one of the problems of integrating wind farms into power network. Okay? And the next thing is so-called Ferranti effect, which is interesting thing. So if you look at this equation, so normally you would expect this is the flow of the real power, and reactive power would flow from power system to the load. But what would happen if either X was here very high, it means you have a huge capacitor, or the load was capacitive? That what might happen, that the Q changes the direction. If Q changes the direction, the voltage drop would be negative. It means that the voltage at the receiving end could be higher than the voltage in the sending end. And now coming back to the question of this underground cables. So remember, underground cables have huge capacitors, which are here neglected on this diagram. So effectively, you connect the huge capacitor over here. So what happened was, so this Ferranti first discovered it, and it's actually anecdotal evidence why voltage is 11 kV. Standard distribution voltage is 11 kV rather than 10 kV. Would you think, wow, 10 kV is a nice number, right? Why is it 11 kV? Apparently what happened when the first distribution line built in this country by Ferranti, which connected London to somewhere else, I can't remember where, it was by means of DC cable, not DC, underground AC cable. And when they connected it, they discovered that the voltage generated by the generator was 10 kV, voltage at the end of the line was 11 kV. Which was surprised because they were thinking in terms of the DC network, well, the voltage goes down. Here voltage would go up. Why? Because when there is no load connected to it, because there was no load current flowing through inductance, there was only strong capacitive effect, which increased the voltage to 11 kV. So this is referred to as Ferranti effect. So the voltage at the receiving end could be higher than the voltage at the sending end, if there is a lot of capacitance in the network. Okay? So this was just to give you physical understanding between different models, and then use this model and the whole power network modeling. So not single line, but the network as the whole. So this is this power flow analysis. For the power flow analysis, what we want to do, we assume that we know the real and reactive power injections. Injections, it means generation or demand at every node. And what we want to calculate, we want to calculate power flows in every single transmission line in the network. So in generation, well, we assume that the output of each generator is determined by the market, or wind power is determined by the forecast, and we expect, okay, so this will be the generation pattern. This is how much power will be generated at every node. And demand is predictable, or used to be predictable. Again, prediction, and you can calculate how much is demand at every node. And the question is, so we want to calculate the power flows, but first we calculate the voltages, magnitude and angle at every node, because if we know the voltage and the magnitude at every node, we can calculate the current, difference in the voltages divided by the impedance. And if you know voltage and current, by multiplying voltages by complex conjugate currents, we can calculate real and reactive power. So this is the general framework. So the solution to that problem is so-called nodal voltage analysis. So if this is the equivalent circuit of the network, so basically, so this is the nodal admittance matrix multiplied by the nodal voltages must be equal to the current injections. Sorry, forget about this for the moment. So this is the nodal admittance matrix, which combines all the information about the network. These are the nodal voltages, and these are the current injections. It means how much current you inject or withdraw from the network. Everything here is a complex number. So voltage is represented as the complex number. Current, so this is the admittance, will have some magnitude over here, and inductance. And those elements, so this is the nodal admittance matrix. So the elements, you can prove that those off-diagonal elements are equal to the inverse of the admittances of the actual line admittances, R plus JX, while the diagonal elements are equal to the sum of the admittances connected to each of the nodes. In power network, we talk about admittances 1 over Z, because you multiply complex numbers. It's easy to multiply complex numbers than divide complex numbers, but it's basically the same thing. So if you form those equations, first a few words about those admittance matrix. So once again, if you look at, let's forget about capacitances for a moment. So if this is the model of the transmission line, the actual admittance of the line, it will be 1 over impedance, R plus JX, but the admittance, it is, so the admittance, the element of the admittance matrix, it is 1 over the actual admittance, and the diagonal element will be sum of the admittances connected to this node or that node. And if those capacitors are neglected, that the diagonal elements are equal to the negative sum of diagonal elements. Now, in graph theory terms, the admittance matrix is the Laplacian matrix. And actually, it took me about 1 year of collaboration with mathematicians to realize that thing when they talk about Laplacian. It's actually the admittance matrix, because you can represent it that way. And I think anyone familiar with graph theory will immediately recognize that this is the weighted Laplacian matrix. The actual Laplacian matrix is here when those will be diagonal unity. Basically, you neglect the values of the admittances. The admittance matrix is singular. You can easily prove it. One way of dealing it with, we assume that the voltage at the reference node is known, usually nominal, and the angle is 0. It means we can neglect one element, one row and one column. We forget about this one, we forget about this one, and that removes singularity of the admittance matrix. And now let's go into the nodal equations, which I showed it was voltages and currents. As I said, we operate with real and reactive power. So let's go now to real and reactive power. So if the voltage equations are I is equal Y times V, we can calculate the current from this equation, and then we can calculate real and reactive power as voltage times conjugate current. So we have kind of complex equations. If we separate the real and imaginary part, we get the familiar power flow equations. So over here, VI, Vj are the voltage magnitudes. Delta I, delta J are the voltage angles at nodes. Gij and Bij are the real and imaginary parts of the elements of the admittance matrix. And there will be those elements will, if we have over here some resistance connected to the node, which usually we don't, and this is the capacitance in the model. So these are the familiar, so this is the full form of AC equations. So if you look any of the textbook, and if you've done any power flow modeling, you should recognize immediately those equations. But these are a little bit complicated. So now let's go through those DC network model. I was talking about that with respect to just one line. So because it's nonlinear, we can linearize it. Basically, take the
Can I ask one question?
Sure.
So when we go back, this is all based upon the model where a transmission line is always a resistance followed by a capacitance.
Resistance, inductance, capacitance, pi. So you're right. So this is the model pi equivalent model. So now I'm trying to simplify it. So this is the most accurate model. Okay, when you want to model everything. But now let's go into simplifications which are useful for some simplified analysis. So first, before we go to that, well, that model is nonlinear. So of course, what we do, we took Taylor series expansion, because there are simple sine and cosine functions. You can just about do it. So if we linearize it, so this is the form of the equations. So it will be the Jacobian matrix, which are the derivatives of P and Q in those equations with respect to deltas and V's and voltages and different angles. And of course, you solve those equations using, for example, Newton-Raphson method. And if you choose your starting point, which is reasonably close to the solution, you'll get a good result. Although Bert attacked me at one point when I said that, said, "Oh, it's rubbish. Newton-Raphson not always gets a unique solution." But the point is that those type of modeling is run usually by power system operators, and they know that given conditions, your starting point should be in that region, and then you get the solution. So of course, Newton-Raphson may lead to non-unique solution, but if you start it somewhere away from the answer, if you start it reasonably close, you're fine. Usually those equations you can get a better form as you get symmetrical Jacobian submatrices. So those submatrices will be symmetrical if you multiply m and k by voltage magnitudes. Means here you multiply by the voltage magnitudes those elements on the right, and then you have to divide them with the voltages by the voltage magnitudes, and those matrices will be more symmetrical. But this is slight modeling modification. But the most important thing is how to get to this DC power flow. So once again, we have this model, and we have this model. Basically, we neglect all the, we assume that the voltages are close to nominal, and we neglect all the elements, all the resistances. First of all, problem reduces by half because we have only real power equations. We forget about reactive power equations. And if you do the simplifications on the equations which I've done before, we have this kind of simple form, which is the same as before. You remember, before it was sine delta I minus delta j divided by x. B is 1 over x, so it's the same thing. So this is the nonlinear DC power flow model. If we assume that those angle differences are small, of course we will get the linear model, which is quite often used by analysis. But remember, once again, you neglect resistances, so you don't have transmission losses, and crucial assumptions, those angles have to be small. So for a heavily loaded network, it will not hold, because if P is high, the angle differences will be high as well.
So what is the worst, like, I mean, if we made 3 assumptions, right?
Mm-hmm.
And as a mathematician, like, the question is like, why is it, like, is there something in between?
So something in between is this one.
So that's the most important one.
Yeah.
So like, keep the side functions. Like, engineers would be most happy if we can reduce the number of assumptions from 3 to 2, and that we can still do the same.
That's what I'm saying. So that's why I'm saying, if you can keep it, you know, it's still half of the original problem, it's still simplified, but at least you have a sign function.
Can I make 2.5 assumptions by having like delta I minus delta j to the power 3?
Well, yeah, of course. There are some models when you have, basically you do the Taylor expansion, you have additional terms. So you replace the sine function by the quadratic function. Yeah, you can do it, of course. Oh, since you talked to me, I just now remember something which I forgot to mention before, which is the question of so-called decoupled load flow. So if you look at the full model over here, that the Jacobian matrix has 4 submatrices, because we have real and reactive power, voltages, and angles. You can get a simplified form of that, so-called decoupled load flow, because remember, real power is driven by the flow by the angle differences, while reactive power is driven by the voltage differences. So we may neglect off-diagonal terms over here, m and n. And so basically, rather than having one complex combined equation, we have 2 separate equations. Delta P is equal H multiplied by delta delta, and delta Q is equal K multiplied by delta V. So that used to be quite often when computers were not very powerful, because you wanted to just, you didn't have so much memory, but some people still use it. And I'm mentioning it because Bert mentioned it to me, that people use sometimes this so-called decoupled equations.
So I saw a paper where either n or m was already.
That's right, and you can neglect just one of them or both of them. So the number of those simplifying assumptions which you can make, and as I said, that's fine as long as you understand the consequences. So for example, if you use the linear model for a heavily loaded network, it's wrong, because the angles are not small, and you cannot model anything approaching stability limits. Okay? So that was the real power flow. What about if we want to model in the simplified form the voltage and reactive power flow? So, as I said, in mesh transmission networks, basically if you want to solve for voltages, you have to solve AC equations. There's no way around it. Maybe some simplified form like this decoupled thing, but you have to do it. But in distribution networks, you may take advantage that distribution networks are tree-like, which means that you can get the solution working from the end of the tree going up along each of the branches. So for example, if I have my equation for the voltage drop, which I introduced before, you can work on that equation starting at the end of the tree and going up the tree, calculate those delta V's in a recursive way, and going up the tree so you can calculate the voltages. More general form of that is so-called dist flow, which was derived first by this paper by Baran and Wu in 1989. So the equations look like that more or less. So you have equations for both real and reactive power. Again, this is distribution network only, assuming radial structure of the tree. So the number of recursive equations, you start at the end, you calculate real and reactive power and transmission losses in a recursive way going from the bottom. So in those equations, k is a consecutive known number. So those k has been numbered according to the order in the tree. So it's not any numbering. It is numbering according to the tree. So PQ, XQ are the power flow from node K to node K plus 1. These are power demands. Sorry. So if you start at the end in a recursive way, you can calculate both real and reactive power and the voltages. Here you can see equation for the voltages. So this is the dist flow. I think Kostya Turisin likes it, and he had a number of papers about it. Okay. So again, you can understand, you can do all those tricks, but remember simplifying assumptions. Yes.
So there's like a further simplification in the last term. You can ignore also the losses, right?
So, yeah. So this is needed to model the transmission losses. So this equation allows you to calculate the voltages, and you take into account also that last component is basically the transmission loss.
Because you can ignore those as well.
You can ignore?
Oh, yeah, what is your opinion if you ignore that last term?
The last term. Yeah. Then you don't take into account transmission losses, but remember again in the distribution network resistances are higher, right? So you can get away with neglecting transmission losses in the transmission network because resistances are low. Distribution network, not really.
Yeah, Angelos is doing that. But we are trying to not do it actually.
Yeah, there's a number of tricks you can do around it.
The math gets so much easier if you ignore it.
Yeah, I know, but you ignore physics as well, so which is not very good. And then is optimal power flow. So, well, most of you have done some elements of the optimal power flow because mathematicians love optimal power flow because there are issues of convexity and all kind of nasty things.
Only Americans.
Okay, there you go, the Americans.
That's right.
So this is just to remind you. So basically, the problem is minimize the cost of dispatch subject to network power balance equations. So you minimize some cost function which is connected to the loss of generation, subject to the nodal power balance. So these are the. So this is the first Kirchhoff law. Power in must be equal to power out, subject to the power flow equations, which are the equations which I've just covered, and subject to the technical generation limits. Line capacity means the power flow on the line has to be less than maximum. And remember that the power flow means both real and reactive power because that's the thermal limit. Both real and reactive power flow causes transmission losses. And there will be some voltage limits and some angle limits as well. So it is the constraint optimization problem. Again, mathematicians love it. Just one, I'm not going into solutions because plenty of books and papers. I'm just showing it to you. But the point which I really want to make, and it links to my previous lecture, is that quite often people solve just OPF equations. Remember, in the actual power system analysis, system operators never solve power flow equations. They will solve n so-called security constraint optimal power flow because you have to take into account n-1 security criterion. So you have to make sure that the power flows are below the limits, not only assuming that everything is fine, but also it will be below the limits if one of the elements trips. So which is a little bit more complicated. Well, simple example. You have let's say thermal limit of two parallel links is 4 gigawatt. That means secure loading is, of course, will be not 8 gigawatts, summing the two, but it's only 4 gigawatts, because if you assume that that line trips, and let's say this is radial connection, all power will flow through one of the links. So the security constraint OPF problem is similar to OPF, but you need those, you will have additional constraints to making sure that if one line trips, then nothing will happen. There's a question also during the break about those emergency controls. So this is example, for example, how again the national grid maintains, because we can think this is Scotland, this is England. Your power flows from the left to the right. Well, that's actually from the north to the south. And this is the situation. We have two links between Scotland and England, one on the eastern coast, the other on the western coast. And what happens if one of the link trips? All power would flow on the other line, and that would limit the safe security limit. So they have this so-called inter-tripping. It means scheme. So it means if one of those links trips, that would be overloaded. The other link would overload it. So that immediately trips one of the power stations which is on system A in Scotland, to limit the power flow on that line to whatever the limit is. So-called inter-tripping. Okay? So remember, system operators determine always actual dispatch by n-1 security OPF rather than OPF. So you must not forget about those security constraints. But it's static and conservative criterion, so the question is how to do it clever. Any questions? The remaining 15 minutes I'll talk about dynamic power system modeling. And my main source will be one of the books which are available on the market. You may notice the second author of that book. And actually the third edition is coming out probably later this year.
You recommend us not to buy this one?
Of course. Whichever. Actually the third edition, you know, I didn't contribute much to the third edition, so this is and the third author has retired, so it will be Jan Machowski and another friend of ours who are working on the third edition. No, but basically what I'm saying about it, because that book is written with the view like my lectures today. It means concentrating on the understanding rather than just giving equations. So there's a lot of kind of physical explaining why the things are the way they are, rather than here's equation and this is how you solve it. Okay? So the last 10 minutes I go very quickly, well, everything you need to know. I'll just give you oversight of the dynamic modeling equations without going into details, so you understand why you have different models, dynamic models in the power system. I will concentrate on traditional synchronous generators rather than wind power double-fed induction generators or PV panels, because those synchronous generators determine still characteristics of the power system. So the first thing is that you saw the diagram before for power frequency, frequency control. So as I mentioned before, if you look about dynamic analysis, when you have a sudden disturbance, those links, strings linking those generators are springs. So you'll have some oscillations. So you need some models of those generators, because normally they kept together by the electromagnetic forces, so they run at the same frequency. If there is disturbance, the frequency will not be the same. So following disturbance, there will be some balance of torques is disturbed, and the speed of machines will not be constant, so there will be some oscillations. So generally, rotor motion is described by the swing equation. I'll come back to it in a second. So if you look at the multi-machine system, it can be approximated by those kind of lot of masses connected by springs, and they will kind of oscillate against each other. The fundamental concept to understand is the concept of the rotor angle. So if you look at, so let's say this is two generators, two rotors, two machines, and they rotate at 50 Hz, the same speed. So there'll be some. So if you look at some line drawn on those rotors, they rotate, but they rotate with the same speed. So again, there'll be some angle between those rotors. And the angle will be, if the speed is constant, the angle will be constant. If the speed changes, the angles between the rotors will change. And so this is the fundamental concept to understanding for stability analysis. So this is the rotor angle. Angle between a rotor and synchronously rotating reference axis. So imagine this axis rotates at 50 Hertz. Rotors also rotate at 50 Hertz, but there is angle between them. And if there is any disturbance, speeds will change and the angles will change. So this is the whole concept of this analysis. Again, remember that the rotor angles are not unique as before, but the relative rotor angles between two generators will be unique because they are relative. So we represent those rotors. We can again represent as the phasors on the axis and the angles between those phasors. So the fundamental equation is that the speed will be derivative of the changes of the rotor angles. So if the angle increases, it means speed of that particular generator goes up. And the fundamental equation, which is basically second Newton's law, is the swing equation. So in steady state, angles are constant. It means those derivatives, two derivatives, will disappear, and mechanical power produced by the generator is equal to electrical power. If there is disturbance, there will be the second order differential equation, second Newton law. So if there is a difference, which means that this mass moment of inertia multiplied by the second derivative of the rotor angle will be equal to the difference between mechanical power and electrical power minus damping power. So this is rotor angle, mass moment of inertia. Pm is turbine mechanical power, and we assume that it stays constant because what we are talking about, we are talking changes kind of second. Mechanical power from the turbine cannot change that quickly because it's a lot of thermal inertia. So mechanical power cannot change quickly, but electrical power flowing down the line, for example, can change almost instantaneously because that's electromagnetic phenomena, and they travel with the speed of light. So we can assume they change almost instantaneously. And there will be some damping coefficient. So I think everyone who has touched upon dynamic analysis is working in those swing equations. So swing equation is always the same. Depending on the model, that component changes, electrical power, because you'll have different equations describing the generator. So as I said, turbine mechanical power is assumed to be constant within the framework of a few seconds, but PE may change almost instantaneously. So that's why we have different synchronous generator models, because there will be different those PE components. So the key is understanding modeling of the synchronous generator. And the steady state model is different than the dynamic model. It means shortly after disturbance. It means if you have a short circuit, for the first few seconds, the model will be different than in the steady state. And I will go and I'll explain it why. So once again, swing equation stays the same, but these equations will be different depending on the model. So first you need, I'm sorry, I think I'll run out by about 10 minutes. So if you have to leave, by all means leave. So first I need to tell you a little bit about physically what does it mean synchronous generator. So it will have a stator, and inside is rotating rotor. So on the stator, as we talked before, it will have three-phase winding. Here is one phase shown. So it will be three phases. And so we call it armature winding. It carries the load current. And those, you can prove that this three-phase stator winding produces rotating magnetic field inside it. Rotor is rotating rotor, and it has some additional winding, which DC winding, which produces magnetic field. So this is effectively an electromagnet. That current which flows on the rotor, this DC current, is called armature current, field current or excitation current. So it will produce magnetic field. And the principle is very simple. If you rotate this rotor inside it, it will produce voltage on the stator, which I showed you before. Additionally, which are not shown here, there will be some so-called damper windings, which will try to prevent the oscillations. So I show you the swing equation, there will be some oscillations, and the damping to damp those oscillations will be provided by additional windings on the rotor. Also, the rotor can be round. It means that the magnetic air gap between the rotor and the stator is constant, or it can be so-called salient rotor, which is, so this is the round rotor, and this is salient rotor with two pairs of poles actually. As you look, so the gap is different here than there. It will have some consequences for our modeling. So in the steady state, let's start from the steady state because it's the simplest. So in the steady state, we model the generator by electromagnetic force, electromotive force EF, which is the driving voltage. The name is, proper name is electromotive force, but you can think about the voltage. The reason for that voltage is that when the rotor rotates inside the stator, it will induce voltage. So the induced voltage EF is the function of the rotor currents, the excitation current, the field current. And if you look at it, so this is the terminal voltage. So this is EF, the driving voltage. This is the external voltage. And we have seen this kind of circuit before when there's just X between the voltages. So immediately we can get the equation of the electrical power produced by the generator as EF times V divided by X as synchronous reactance multiplied by the sine of the angle delta, which is the angle between EF and V. The key to understanding is that that angle delta here between EF and V is also a mechanical rotor angle, which I showed you before. I don't have time to prove it, but you can prove it. So that angle delta has double meaning. It is angle between two voltages, phase shift between two voltages, but if you do some further consideration, it will be also geometric angle between rotors. So it has electromechanical meaning, which is fundamental to understand it, because now we can link electrical power model, this is electrical equation, with mechanical model, which is the swing equation, second Newton's law. So that means that power, so you have one equation, that equation is mechanical equation. This is inertia, this is everything is mechanical here. But inside it we have electrical power, which uses the same rotor delta, which is used for the rotor modeling. So now we have different dynamic generator models. And the point is that generator cannot any longer be modeled as a constant reactance, because the path of the magnetic field changes with time. Let's go again between this model. That reactance XS depends on the path of the magnetic field inside the generator. You can prove it quite simply. It depends on the reluctance of the magnetic path. If you go back, let's say here, the magnetic field crosses from the stator to the rotor. It kind of goes that way. Okay? And the reactance XS in this equation will depend on that path. What happens in the following a fault, that the path will change. It means the reactance X will change. So I'll show you. So generally speaking, everything is continuous, but we divide it into three phases, so-called subtransient state, transient state, and steady state. And will be different paths of the magnetic flux inside it due to screening effect of different fields. So first, subtransient state. Subtransient state takes a few cycles. Each cycle is 20 milliseconds. Okay. So what happened? If there is a fault, then current suddenly increases. If current suddenly increases, then basically that magnetic path tries to enter, which is shown by dashed line, the path of the minimum of the minimum reluctance, the easiest path for the magnetic flux is go like that, right? Remember, the nature is conservative, very conservative, and always tries to follow the path of the least reluctance. So magnetic field, if you have two metal lamps, it tries to go by the shortest possible path from one metal part to the other part. So it means it should, if you look at the rotor, it will try to go like that. But inside the rotor we have a field winding and we have a damper winding. And those windings will repel the external magnetic field. All the coils have this effect that they don't like sudden changes in the magnetic field inside them. Like, for example, superconducting coils, well, nothing can change, they'll always stay the same. So initially they'll try to repel. This is so-called screening effect. It will decay with time as the currents dissipate energy, but initially the path will force out of the path of the least reluctance, which is going to go like that. It will avoid the damper winding and the field winding, so it will go through the air gap. Because it will go through the air gap, it has high reluctance, and as it has high reluctance, it will have low reactance, X. Again, using these fundamentals of electrical engineering, reactance is inversely proportional to the reluctance of the magnetic path. Air, high reluctance, low reluctance, high reactance, metal the other way around. Low reluctance, high reactance. So, so basically, because this low reactance, current is voltage divided by reactance, it will be very high current flowing initially. With time, those currents will dissipate energy in both damper windings and the field windings, but damper windings have high resistance. That means that after a few cycles, and then we'll have so-called transient state. And the transient state, the magnetic path can enter the damper winding, but it will still go around through the air gap around the field winding. That means in this circuit, it has a lower reluctance than in this case, because it partially goes through the rotor. That means it will have higher reactance. That means it has lower current. So that effect, so they will have screening effect only of the field winding. And again, after a few seconds, the currents will dissipate in the field winding. That means that the current now can take the path of the least reluctance. It means it will go through like that. It will try to minimize the path which goes through the air gap. And that path will have, sorry, here is a mistake, it should go low reluctance. It means high reactance. It means lower current. So we divide the whole dynamic effect into those three stages. Subtransient state with low reactance, internal reactance of the generator. Transient state, slightly high reactance, low current. And steady state, low reluctance, high reactance. It means the current is low. So if we look at it, so the current will go like that. It will be high initially, then it will be lowering down to the steady state value. That means that if you look at the reactance, it will increase in time. But it's difficult to model the whole thing using these continuous changes. So the common assumption is we divide it into three stages. So in the subtransient state, the reactance of the generator will be X double dash, small. Then we assume that will be transient reactance XD dashed, and steady state will be XD. D means direct axis, because I mentioned before we have the saliency effect. It means magnetic, the air gap is not uniform around, so everything will divide into D axis and Q axis. Oh yeah, here it is. So if you look once again at the generator, we have direct axis, path of the minimum reactance, and the direct axis. So all the reactances will have two components, D axis component and the Q axis component. Again, I don't want to go into that, but just remember that the full model will have more components. So once again, instead of modeling everything changes continuously, we just assume, okay, in the transient state, the reactance is that much, it stays constant, which is an approximation, the same in the subtransient state. So we divide the whole continuously changing process into those three stages. That means we are talking about three dynamic generator models. Subtransient state, when you have subtransient a voltage behind subtransient reactance. In the transient state, we have a transient voltage behind transient reactance, and steady state, we have a synchronous voltage behind the synchronous reactance. As you can see, here we have just approximation, we are just considering changes only along the d-axis, but you'll have similar circuits for the q-axis. I'll just neglect them, just not to overload you with information. So we'll consider those three stages. And the subtransient reactance is lower than the transient reactance, is lower than the synchronous reactance. So now let's go to the swing equation in the model. So once again, this is the swing equation. This is electrical power. So the simplest model, we just assume this is just the voltage behind the transient reactance. So in the transient state, we just modeled. So this is the equation. A PE is equal E dash times Vs divided by a transient reactance multiplied by the sine of the angle delta. Dash signifies that it is transient state. And this is the main model using for the transient stability analysis, which is a few seconds. Because if you talk about losing stability, we talk about it will happen over 2 or 3 seconds. Now, that means if we substitute that equation into here, we'll get this kind of equation where K will represent all the constants. So we have the swing equation with the term over here sine delta. So again, if those changes in delta are small, it's very similar to the standard mass spring damper system, because instead of sine delta we'll have just the delta. So that's why we, as I said, those strings which link generators are springs. There will be some oscillations for small signal analysis. It means when the changes of delta are small. So we can think about generators connecting in the power system as connected by the sets of springs. So it's a lot of results because there's a lot of theory regarding springs that are directly applicable. But remember, this is a linear model. It means we assume that delta is small. What happens if the disturbance is big? If the disturbance is big, we cannot assume any longer that delta is small. We have to use, we cannot use a linear model, we have to add this angle delta, and then a mechanical analog is not the spring, but it's a pendulum. If you look at the pendulum, the force acting is proportional to the sine of the angle, which is similar to what happens over here. And then the phenomenon of losing transient stability is, if you hit the pendulum, so it will swing around, go past 180 degrees, it will lose stability because it will continue to oscillate. The same thing happens with the generators. So the transient stability is when the disturbance is so high that delta will go above certain transient stability limit, and it will keep to increase. I think I'm going for too high, so I just show you the different models. So once again, this higher order generator model. So the swing equation is always the same, but we will have different models depending on the level of accuracy. The simplest model is this classical model. It means we assume over here that voltage is constant. But that voltage, E dash, actually will not be constant because there are some changes in the generator. So there will be the additional differential equation which will describe the changes in the driving voltage E dashed. So that's why it's a third order model, because this is second order model. The n plus one additional differential equations will be third order model. And then the power P which goes into here will be a little bit more complicated. So this is the third order model. Fourth order model, you add two differential equations for EQ dash and ED dashed. Fifth order model, you add three differential equations because we are talking about phenomena in both d-axis and q-axis. Remember, they have two axes. Again, I don't want to go into details. I just want you to understand from the higher level. And the most accurate model is the sixth order model, when you are talking about both the transient and subtransient electromotive forces. So this is the most accurate model. And again, the power E, which goes into equations, will be a little bit more complicated. So in terms, what I would recommend, people mostly work with the classical model, which is, sorry, on the previous slide, which is that model, which is accurate enough. But if you're going, and that it's fine if you're just looking at the real power. If you are looking also changes in voltages, then you may look at the third order model. And John asked me at one point the question because he was interested in the dynamic phenomena. So basically, third order model is the best, is the simplest approximation which you can take if you want to model changes in the voltages, which is one additional differential equation. If you go down, that basically you increase the accuracy of modeling, but may not always be necessary. One thing I just want to point attention to, that as you increase the accuracy of modeling, the value of the D changes, because D models damping effect. For the simplest model, when you neglect any damper windings, that coefficient is high. In those models over here, you model more accurately damping effects. It means that the value of the D in the swing equation gets smaller. And this is typical mistake people make. They increase the accuracy of the model, but leave the D value constant. No, it's not. It will decrease. A lot of details about it. I just wanted to give you a high-level view of what is happening. Now, maybe this is the last slide. I think I'm overloading you. So this is the models of the generator, but if you're looking at the whole power station, you will have, apart from the generator model, you will have the exciter model. It means the model of the how this voltage EF is being generated, which will include, well, a lot of, because this EF over here, it will depend on the terminal voltage, number of things. So you also have the model of the power system stabilizer, which will stabilize those, which will stabilize swings in the power network. And also you may have a turbine model, which will have higher axis. It means so that models the droop characteristic. If frequency changes, this is how the power output will change. I don't go into detail about it. I just give you, just share you about modeling. I also wanted to talk about the stability, but I'm just wondering if I have not overloaded you. Yeah, I think I have overloaded you. Well, the slides will be available, so you can have a look at them. I don't want to go into details. Sorry? Well, I will send to Almut and she will circulate it. So you can have a look. I don't want to talk about it. The rest of it, I'm talking about this difference between different oscillations, stability problems. Sorry?
If we have read your book, do we know everything?
Kind of. Well, there are a number of books. My book concentrates on understanding. The Bible of Power System Dynamics is a book by a guy called Kundur. You have all the equations, everything, detailed model of everything. But with Kundur, it's excellent, but you have to be an electrical engineer to understand it, because it's quite detailed modeling. With our book, we try to be, in between. Try to explain things without going too much into heavy modeling. The remaining slides are about different power system stability problems, but I think I have overloaded you. Talking about transient stability problems and the steady state stability problems, but I think that's too much. I'm happy to talk about it if someone approaches me. Okay? Any questions? No questions. I think that was too much. I think I have overestimated, as usually, the amount of time. Underestimated the amount of time. Thank you. I'm here until Thursday. I'm leaving around lunchtime on Thursday. I might not be here on Wednesday because my wife is with me and she wanted to nip out to London. So I'm not sure if I'll be around. But I'm here today and tomorrow. and on Thursday. Okay? And then I'll be away next week, but I'm coming back the week after. Thank you.